Good afternoon, everyone. And first, I would like to thank organizers, Professor Debashish, Professor Maiti, and Ambarish, to give me opportunity to present my work, as well as meet my old and new friends in this platform and young students also. So, and I'm sorry, this title is not the same as in the abstract I have sent, but this is also new, at least in this room. So during my talk, I will discuss various different terms here. But in very brief, the inhomogeneities means here some differences. An active system, I think everyone in this room now knows, because there was already few talks before my talk. And before my talk, maybe I can just say one word conclusion for my talk also. Inhomogeneities are not always bad, they are also good somewhere. That's what the focus of this talk. So before starting my talk, I would like to acknowledge who are the students and faculties and colleagues who has contributed in the work in active matter with disorder or inhomogeneities. And the first few list are the students who has actually contributed in the active system with inhomogeneity or disorder. And today I'm going to mainly talk about the work by one of my graduate students, Samir and the Jayaprakash Singh. And these are the other students who are also working in active and the other statistical system. And in this talk, we collaborated with our colleague, Professor Giri in IIT-BHU, and I have also done some work with disorder in active system with Professor Sanjay Puri, which I am not talking here. And I really want to acknowledge the DST sir for the financial support. This is a very brief outline of talk, which is not in much detail. First, I will give you a motivation about active system, but which I don't need, maybe Rumi has already given a very detailed, but still I will show you some pictures. Then introduction to active matter, that will be basically the main results, which are the key results which is not present in general in passive systems. And then some of more result when these active or whatever self-propelled particles, when they are in the clean environment, when there are particles and well-known things and there is no randomness present. Then I will directly come to the intrinsic inhomogeneity. We have also done something in extrinsic inhomogeneity, where the inhomogeneities is present externally. I will come to that, but that I am not going to focus today. And then conclusions and future aspects. This is a very overview of the things, why to study active matter, and this is already now known in this community, that this system starts from very small scale, we have seen from cellular scale in this meeting also, to many cells level on the level of bacteria and then fish school or frogs or even live and dead, both kind of object, copper rods and all. The interesting is that we have a many particle effect and collectively they do various things which is not present in general in equilibrium system, and they can do various different things. There are based on the symmetry of particle, this is not only, but there can be other things also I will come to. There are two kinds of particles in general. The particles, first of all, how we will define that they are active or self-propelled. They have to have the particle itself, each particle have to have some kind of asymmetry. It can be either shape or chemical or anything else or mass. There should be some asymmetry. But at least in this slide, it's only the shape asymmetry, these pictures. Then I define the self-propelled particle or active particle, which are the basic ingredient of these active systems. So they are particles which are asymmetric objects, and they actually, because of such asymmetry along their one of the axis, they move along that direction, along, maybe you can say that long direction or whatever. Based on that asymmetry, if they have a head and tail asymmetry, I will call them polar, and mostly bird flock, fish, ants, or various things, vehicles, they can be thought of like a polar entities. But there are other self-propelled particles also which cannot distinguish between forward and backward, or they are equally probable for going forward and backward. They are called apolar. The many cells comes into this category that they are apolar. And depending on when they are put in collection, they can align because of, or they can arrange themselves because of crowding effects and all. If these polar particles align in this fashion such that there is a non-zero velocity, this can be called as the flocking or the ordered state. And if they arrange in this manner that they don't distinguish between forward and backward, that can be called as apolar state, where the velocity is 0, and something called the nematic order parameter, which can be non-zero here. And obviously these apolar particle can also arrange themselves such that obviously V is 0, but the Q can be non-zero. So there is a two kind of particles and two kind of ordered state if they are arranged in the dense environment or if they are in the large in numbers. So, but for today's talk, I mainly focus on the polar particles, and maybe polar order or not, I will come in the next part of my talk. Okay, and this is again maybe repetition here. Yesterday also we learned that for understanding or studying these problems, since they are active, we cannot write the directly and Hamiltonian and solving the free energy. So we have to start with some other approach, and this is a very basic or maybe the very nice approach to study. We can start with the rule-based model, and that makes our life much more easy. So this is a model which Rumi has also given. There is each particle can be thought of as a point particle, and they are defined by their position on this two-dimensional substrate. It can be also defined in 3D, which is denoted by xi at particular time t, and I is the particle index. And each particle is associated with an angle, which is like for the spin degree of freedom, I can give an orientation. And these particles are self-propelled, that is given in the second term here, that they move along their velocity direction, vi, which is a constant speed times the unit vector along the theta. And they also interact with their neighbors in some small radius, and getting the mean orientation of all the particle in the neighborhood, and when then it's not completely deterministic by the neighborhood, there is some randomness, and which is controlled by this delta theta. So then we can see in this model, if I don't have a second term or the self-propulsion speed is 0, then the model is like a xy model of lattice, not on the lattice. I'm not arranging them on the lattice, but one can define also the model on the lattice, and very well studied, and various different things have been found. Yeah. Theta should also be theta I, right? Yeah. Theta, left hand side theta should be theta I. Right hand side is the average one, yeah. The model is not very similar, but it's similar to the equilibrium XY model, but it's called the moving XY model, and it shows various phases and phase transition. And one interesting phase transition or phase is for the small delta theta, and the density comes through this interaction. If the density is high, then there will be many particles in this interacting radius, and for high density and lower theta, system form this kind of ordered state, which very much look like a herd moving in one direction. And if low density and high noise, then it's actually in the disordered state, which is this picture, something similar. Otherwise, you can get some intermediate phases. Okay. What are the key results? One is this order-disorder transition, which we cannot find in the XY, equilibrium XY model. In the two dimension, we have only disorder to a quasi-long range order state, but we have seen that in bird flock or in animal herds, there is actually almost everyone is moving in one direction. That is actually a long range ordered state. You don't need to measure the order parameter. You can also observe this, that there is a long range ordered state in two dimension, and they are moving, at least animals are moving in planes. It's a two-dimensional system. So there is an order-disorder transition as a function of eta, which is difficult to control in experiment, but the similar transition can be also found as a function of the density of particle, and that is also first order phase transition. For lower density, it is disorder. This will be like a row inverse then, disorder, and for the higher density, it is an ordered state. So there is a long range order to the disordered state transition as a function of noise and density. And this transition have been found to be first order. Initially in the V-check model, it was a continuous transition, and later on there was some different studies on the working on the different kind of noise, and it was found to be a first order phase transition in numerical studies by the Setes and various other groups now. This transition is a first order phase transition from order to disordered state. And there is a second interesting feature about these systems, that if we are measuring the density fluctuation in some small box here or the area. So suppose I keep a small box here and I just measure the density fluctuation in this small area over the time in the steady state, and system is in the ordered state, it's not undergoing a transition from disordered to ordered state, then the density fluctuation in the steady state is actually much larger than what you expect in the equilibrium. In equilibrium, we expect this sigma square will be proportional to n, irrespective of what dimensions you are, provided you are not near transition, and we are not near transition here. But here it is much larger than that, and exponent is close to 1.6 for this polar system, and actually for apolar system it's exactly 2. So these are the two key results of these systems, and there are various other interesting things, but these are the two key results. Now I will directly come to the active system or these particles if they are placed in the presence of inhomogeneity. And there are also experiments. This is not only experiment, there are various other experiments also. So this is one experiment by Morin's group in 2017. In this picture, I am showing the y-axis here on the downward direction, the increasing the density of obstacles, and these dots are actually the obstacle present in the path of the self-propelled particle, which are not shown here in a point manner, but there are particles. And these obstacles are actually obstructing the path. And then in the color, it actually shows the current along this direction. So there is an ordered state if there is no obstacle, and that ordered state is moving in all the particle, majority of the particle is moving in the positive x direction. And as the density of this obstacle is increased, we can see in the bottom direction, then this current is actually decreasing. For very low density, they are able to pass through because we see there is a large current. But for high density, we see there are mostly zero current. So that is a very clear picture that this obstacle or the disorder is obstructing the path, and it is actually breaking the long range ordered state present in. Yeah.
Static ones or dynamic?
These obstacles, they are static. But even for the dynamic one also, you will see that there is a destruction of order. Yeah. So this long range order, the state is not present for the finite obstacle, or actually for the moderate obstacle density. That is the key result here. But it's not like the obstacle is always bad. Even in the numerical simulation in 2013, this picture shows this axis is actually the order parameter, or you can also say the measure of the average of the heading direction of all the particle. If everybody is aligned in one direction or moving in plus x direction, let's say, then this number will be close to 1. If they are all completely random, then R will be close to 0. And this axis is the noise strength or the delta theta in the V-check model, one can say. And this is the obstacle densities axis, the rho naught. For zero obstacle density, there is a transition like the V-check model, that there is a order to disorder transition as a function of eta, which whatever the V-check and others have found. But for the finite obstacle density, these different curves, actually it looked like, in general we have an impression that the lower the noise there should be the higher order, and higher the noise there should be low order. But for the finite obstacle density, to some extent, by increasing the noise, there is some kind of a non-monotonic feature, and that is actually the title of the paper, that for the finite obstacle we need an optimal noise to facilitate the flocking. It's not like always the obstacles are destructing the path. To some extent they also ease the passage. That's what this non-monotonic feature shows you. And there are some other work also where there is actually some measurement, or there's some results to show that how many such non-aligner or randomness we require to break a well-ordered flock, and that is this paper, and there are various other work. These are just a list of few. Okay, so now I'll directly come to what we are looking forward. So this kind of obstacle, where the obstacles are placed in the medium, either in this one or in this work also, that I call them as the extrinsic obstacle, and they are very important because in almost every path you move, there are obstacles. But there are also intrinsic obstacles or intrinsic disorder. That is basically the differences among the particles. There is no physical obstacle present, but everyone has their own difference. Not everyone is same in their behavior. That I call as the intrinsic disorder. That's not present in medium, but that present in the particle itself. Like in the V-check model, we assume that they're all moving with the constant speed, but that's not true. They can move with different speed, or they have a different ability to move. That I will call as the intrinsic disorder or intrinsic inhomogeneities, and for most of my talk today, they are quenched. If I am like, I have some feature that's always present, I'm not going to change my behavior because of my neighborhood. That is also interesting to see how my behavior changes with my surrounding or neighborhood, but that is not part of this talk again. It's intrinsic, and how one can think of in that in some simple language, that maybe some the particles are moody in nature, some particles want to align, have a more alignment tendency, some have the less alignment tendency. Why to everyone in the V-check model align with the same strength? Or maybe the particle itself are different sizes, or maybe everybody don't want to see the 2 neighbors, 3 neighbors, someone wants to see no neighbors, they don't want to interact at all, or different things. I will mainly focus on this alignment feature and this different size in today's talk. Okay. So now I'll come to the first part of my talk. The first thing where we are actually introducing the inhomogeneities as a bond disorder. And this name or this nomenclature we adopted from the XY model with the bond disorder. But few days back I realized actually it's not a bond disorder, it's a site disorder. But now the 3 papers we have published and referee has not reminded us, so that is why I have not changed this. It's a bond disorder, and I will not tell you it's a site disorder in this talk. Well, I will not explain you why it is a site disorder. Okay, so let me just explain the model to you. So this is like in the V-check model, this is my the ith particle, the green one, and there is some small interaction radius drawn around the particle. And every particle inside it, each particle inside it is going to influence the alignment of this green particle. But in the V-check model, each of the particles inside this circle is going to influence in the similar fashion. But now I have labeled different colors with different particles, and depending on the colors, they are going to influence the green one. It's not like the green one is having some color. Green one obviously have a color, but it's going to influence some others. Okay. So like red particle which has and the shape of the particle is, this circle is just, they are still point particles, circle is just drawn to show the particle. So this red one which has the largest arrow is going to influence more to green one, and this I think the violet one has the shortest arrow, which is the smallest arrow, which is going to influence the least one in the circle. So this each particle you can think of, they have some chemical signal and they are sending different strength of that signal to influence the green one. But once these numbers are given, the signal strength is given, that is fixed to each particle. I am not going to change during my course of this study. And then after that, and I will come to how this different things are taken in this mathematical model. But before that, suppose I want to compare this with the V-check model where everyone was having the same unit strength. Yeah. The
colors are assigned for each pairwise interval?
No, not pair. Each particle have their own sense of signal to give. It's just pairwise also can be done, and actually then it is a bond model. That is why it's a site model. Yeah. Okay. So now if I compare with the V-check model, in the V-check model each particle will have a unit length, and these actually arrows I have drawn according to their direction but making the unit 1, and then the resultant of it, which is the sum of all these unit vectors, will be in this direction. Noise is not added in this resultant. But if they are having a different length, like in this one, then the resultant in this green one, and there is a difference just to show that there will be some difference in it. And if you look at the model in detail, actually you will find that this green will be always closer to the particle orientation. It will have, you can say in some sense, is more resistant to change its orientation compared to when it's a uniform case. But that needs some detailed analysis, I will not come to that. Now coming to the mathematical way of writing this, first of all they are all self-propelled, they move along their heading direction and I with unit vector obviously, the speed is not changing, V0 is still same. They only take care of their direction and move in that direction with a constant speed. But for alignment with their neighbor, they take care of these different strength, and that different strength is obtained from a JJ. This is otherwise in the V-check model it's a 1, is obtained from a distribution which is a uniform between 1 minus epsilon by 2 to 1 plus epsilon by 2. And epsilon is my parameter for disorder or inhomogeneity. For epsilon 0, it will be V-check model kind of alignment interaction, and the epsilon maximum value I can take it 2 when it will be going from 0 to 2. So if, and mean is around 1. If something is less than 1, it means I have a lesser alignment tendency. If something is greater than 1, it's a larger than the V-check one. Okay, and then the noise is added, the eta, the noise strength, this is a number of particle inside the interaction radius, and this is again a unit random vector. And then the whole thing is normalized to make the right hand side unit vector. This update is slightly different from V-check. This is called the vector update, but that details is not necessary. Just they are aligning, and then there is some random force, which is with the strength eta. Okay. So now I just, before going to the result, I want to say by introducing this epsilon, what I did is I am saying with some particle I am going to align more, and with some particle I am going to align less. I have introduced both positive and negative feedback in the model, and end result is that the positive feedback becomes more important compared to the negative feedback. So there is some positive results out of it. Okay. The model is clear to everyone? Okay. And the system is simulated in the two-dimensional substrate with periodic boundary conditions and all those details. And okay, let's see. Okay. The first thing we also look at the things deeper in the ordered state, but this talk is in the near to the order disorder transition. For all epsilon value, epsilon is my parameter now, system shows a transition. This psi is again a parameter which measures that what is the average, like how many particles on an average align in the same direction. If it is 1, that everybody is aligned in the same direction. If it is close to 0, then there is more or less disordered state, completely disordered state. This psi versus eta, which shows the order disorder transition, and almost for all epsilon, this the black curve is for the epsilon 0, and this magenta one is for epsilon 2, and intermediate is for epsilon 1. So there is order disorder transition. We also check that the order state for all the epsilon value is a long range ordered state. The long range ordering is not disturbed because of such kind of inhomogeneity present. But if I look at the nature of transition for different epsilon, so this is the near the transition. First of all, the curves also look much less steeper compared to the black curve. That gives a signature that the transition is becoming continuous. So then we look at the probability distribution of order parameter near transition, near this critical region. For the epsilon 0, there is a very clear bimodal nature that shows it's a first order phase transition. But for epsilon 2, it's a very broad distribution with huge fluctuation that shows the order parameter as a huge fluctuations, and that is a signature that is a continuous transition. The long range ordering is not disturbed, but the order disorder transition has become from the first order to the continuous type. And then we have also calculated the Binder cumulant, which also shows that there is a sharp dip for the epsilon 0, and as I go increase epsilon, there is a continuous variation from 2 by 3 to 1 by 3 value as I go from order to the disordered state. Okay, so this is the first, yeah. If I take larger, then there will be anti-alignment. We had some result, but that's not part. That you will get some other phases, antiferromagnetically aligned and those things. Yeah, but not in this one. Yeah, because then this number will be negative also. That will like anti-parallel alignment or something. Yeah. Okay. The first result is that the long range order persists and order disorder transition changes. But there is one more thing which is important here, that near the transition, if I zoom in, that in this transition region, the ordering is enhanced in the presence of epsilon, finite epsilon. So we can see this magenta curve is above this black curve. For constant eta, for finite epsilon, we are getting the ordering is larger than for the 0 epsilon, and we are going to focus on that and trying to understand what's happening. The second quantity we look at, this order disorder is, or the ordering state, or the flocking in one direction is not the only interesting thing. We also look at how the density is behaving, how the particles are clustering in the system. This picture is a density snapshot. This color actually shows the number of particles in a unit square box. So this 50 means actually they are a very high dense clusters there. And for different epsilon, again this is epsilon 0 and this is epsilon 2 and middle one is epsilon 1. One thing we find that for the 0 epsilon there are very dense cluster, but as I am increasing epsilon, the system is becoming more homogeneous in terms of density, and that is again near the transition. The system is becoming more homogeneous in terms of density, and that is actually the answer to many things we are going to come in the next slide. So now we actually want to answer why there is an enhanced ordering near the transition. For that, we just did one small, maybe the computer experiment to our simulation. So we just try to thought maybe the enhanced ordering because and there is a homogeneous density as well. Because of that, maybe if I give some perturbation to my system at some point, it should be getting to all other particles quicker than when there is epsilon 0. For checking that, what we did, we had a well-formed ordered flock. We reached to the moderate ordered state, and then we suddenly place some particle quench in some direction. That is they are acting like an external field at random locations. And then we look at the other particle response with respect to that quench direction. So very soon, more or less, everybody will be aligned in that direction because there is alignment happening. But we just want to see how is that response time for different epsilon. So we calculated the orientation autocorrelation of other particles, average over all particles, with respect to this quench theta. This is a theta it. And then theta I0 is their particle's own orientation, which they are going to forget very soon because they are experiencing an external field in the problem. And here we are plotting this orientation autocorrelation function for different epsilon. This black is for epsilon 0, magenta is for 2, and then 0.5, 1 and 1.5. So we see for the epsilon 0, the response is delayed. The quicker they are following, the response is quicker compared to for the epsilon 2, where the response is quite fast compared to the 0 case. And these are all exponential. Using that, we calculated a response time. One can say this TC, and that actually linearly decay with epsilon. And with respect to this TC, we are able to also do the scaling of this autocorrelation function by T by TC, and we find that there is a very good scaling in the problem. Okay. The system response is quick in the presence of finite epsilon. Any perturbation if you give, it will respond faster. Okay. Then we wanted to understand it even better, why it is happening. For that, we started looking at what actually happening in the system. So we actually calculated a quantity which actually taking care of how frequently I am updating my neighbors, because I am giving my information through my neighbor. I might not be able to reach to the other point, but my neighbor can reach, and that can take the information of mine, it's align in this direction and to that. If I am updating my neighbor frequently, then maybe my response is reaching to the far end of the system quicker. I am actually calculating the neighbor update, and this x and this y is the same quantity here. So this is the quantity xt or yt is defined in this mathematical form, but what is the meaning of it, I'll explain. And this actually measures the like how frequently my neighbor list is updated. If it is a completely flat around 0, then I am not updating my neighbor at all. But if it is switching forward and backward very soon, then I am actually updating my neighbor frequently. So this is a snapshot of this quantity for different epsilon. From black 0 and magenta is 2. And this shows that there is a wild oscillation, but oscillation frequency is increasing for the finite epsilon. And then using this quantity, this time series, although it's looked quite random, we calculated autocorrelation of this quantity. And this is the neighbor or neighbor-neighbor autocorrelation. And this is actually measure like how long I am correlated to my neighbor. If I am having a long tail to this correlation function, it means I remember my neighbor for a very long time, or I am in the neighborhood of the same particle for a very long time. But if this quantity is decaying faster, it means I am updating my neighbors very frequently. So this quantity also shows an exponential feature. And for the epsilon 0, it's having a long tail. It means my neighbor list are updated in a very delayed fashion. But for the finite epsilon, I am actually updating my neighbors very quickly. And that this again from here I can get that time scale of this decay, and that also linearly varies with epsilon, and again we find a very good scaling. And also using this, actually we can calculate information entropy in the system, which also increases by increasing epsilon. It means in general the information transfer is happening faster in the presence of epsilon. And that is, this is the order parameter versus time near transition, and that shows the system is reaching to the ordered state quicker compared to this black curve, which is for the epsilon 0. Okay. Any questions still here? Yeah. From this update equation in the first few slides, yeah, this is the time. Delta t is 1 here. Is 1. Yeah. And then I'm just looking at different time. Yeah. And things are measured in the steady state. That is constant.
Yeah, that is constant for now. If you change the speed for some other higher magnitude and keep the rule same as it is. So you see that the updating of neighbor will be faster because it's moving with the.
But it will be faster for all epsilon. I think feature will be there, but maybe happening at some other time scale. Yeah. But not very fast. They should be in the V-check model, this speed is chosen such a manner, they should be in the neighborhood for some time. Yeah. Okay. Okay, that is, it's not very, it's not very settled, but what we did is, we are defining the configuration of the system by the index of my neighbor. Suppose I have an n number of particles, then I can be in n minus 1 states, depending on which neighbor, or actually not n minus 1. It's, if I think of a pair interaction kind of thing, n into n minus 1 kind of states. So what we did is actually, this is autocorrelation function, which actually measures or is actually is a view that how frequently my configuration space is changing. We just calculated C log C of this quantity, and with this C log C, this Cn, and subtracted from for the epsilon for the reference case when it is a completely randomized situation, that is delta S. And that we call, because in that manner it's actually the probability of being in the same configuration, C. It's average of log C. Yeah, average of log C. Yeah, the average of log C. Yeah. Okay, any other questions? Okay. With this, I will just conclude this part of my talk, that bond and disorder leads to faster information transfer in polar flock, which is not very trivial. Now I'll come to different thing. So now my particles cannot align. So it's coming to more in the morning talk, run and tumble or ABP kind of thing. So they are active Brownian particles, and there is again a lot of literature. And this first line is basically till now in my presentation there was alignment, but now I am switching off the alignment. But we need some interaction, so now I have given the shape to the particles. So we need some interaction in the finite volume. Okay. And they are called active Brownian particle, and if size of each of these particles is same, then it's well known now that the system is actually shows the motility induced phase separation for some moderate density and higher activity of the particles. I'll come to the equations and then I'll explain in more. But what we are trying to do here, what we did is the same active Brownian particle, but now they have a different sizes, And that is present in mostly in the system. You can have a different, they're not necessary to be all the particles of the same size. And we want to see the impact of that in this ABP system. And we call it the polydisperse mixture. And again, it is an intrinsic because inhomogeneity is introduced in the particle level. And once some particle has some size, it's a fix, it's not going to change. And this is just a cartoon of my system. This color shows the radius of the particle in two-dimensional substrate. They are like a disk of different sizes. This dark blues are the smallest one and dark reds are the highest one. Okay, so this is the model. So we have a collection of ABPs of different sizes. And each particle again defined by its position in this substrate, which is denoted by Ri. And these systems are mostly mimicking the overdamp system like a cells or bacteria. So it's overdamp limit. I'm not going to, at least here I'm not going to see the underdamp situation for this system. And they move along their direction with a speed v0, speed v0, and the EI is their heading direction determined by this orientation. And they also interacting, not the alignment interaction, but now they have a finite size or shape, they are circle or disk. So this interaction is coming from some kind of a soft repulsion, but the form of this repulsion is not very important. You can take some other soft repulsive force and these results should not change. Even I think with the hard sphere interaction also they should not change. So now this is our potential we have taken for the part 2 particle interaction, which is a spring force. It's going to only act if the particles are going to touch, that is this theta function will take care. If they are of the same size, and that is where this polydispersity is coming into picture. If they are monodisperse or the simple ABP with MIPS, then this sigma ij will be just the diameter of the particle, but now it's a radius of 2 particles, sum of the radius of 2 particles. This is in 2D.
So these are like just representative equations, right? I mean, for both the dimensions, are they coupled equations?
This is vector. R is a vector here.
Yeah. So like for both the axes, are there like two different equations, or like they're coupled in these representative equations?
No, they will be coupled because this is also this will be only x component. Now, it should be solved and written in the component wise, but in this F you will have a R.
Yeah.
So
If they are just representative equations.
yeah, it's a vector equation. And anyway for solving this you have to write it component wise, and in each component there will be y also coming because of this R, the scalar R there. Yeah. But for solving you have to write in the component wise x and y. And even in 3D also you can do, but then you need one more theta or phi angle. Yeah. So this is the interaction, and this R, the radius of the particle, is actually taken from a distribution, the uniform distribution, the mean around some R naught. And we have taken care such that in the distribution we should not go on the negative radius, the radius is always positive. And with some, the parameter which takes care of this polydispersity, which is epsilon naught, and the distribution is varying from the R naught minus epsilon naught by 2 to R naught plus epsilon by 2, uniform distribution again. And epsilon 0 is my parameter which takes care of this polydispersity. If it is 0, then it's a monodisperse mixture or simply the ABP model. And for theta updates, it's just a random rotation with some rotational diffusivity dr, and eta is obtained from a Gaussian white noise in the model. And then we can define some dimensionless quantities. This epsilon, epsilon naught, which is actually a polydispersity index. So we define a dimensionless polydispersity, which is a ratio of epsilon naught by R naught. And this epsilon can be varied from the 0 to 1. And this dimensionless activity, which is defined in this fashion here, but again this we have written here the mean radius, but you can think of that for each particle, since they have a different sizes, that there is we can also assign the different activity, dimensionless activity for each particle, where this R naught can be replaced by the Ri. In that manner, I'm not just introducing the polydispersity in size, actually I'm introducing in indirect manner the like a different speed, different activity for each particle. Vi is different for, dimensionless Vi is different for different particles. Okay, is the model clear? Okay, so now, yeah. I said, no, even if you take WCA, you take hard sphere, results, qualitative manner, it should not change. There may be we have some phase diagram also, the boundaries and all can change. But the main thing which I am going to emphasize, that will not change. That should not change. We have checked for WCA, hard sphere, we have not checked. Okay. Now I'll come to directly to the observation. We want to check both the dynamic and the steady state here. First thing, we calculated how the dynamic of the particle changes. We calculated the mean square displacement of particle for different activity, dimensionless activity, which is on the left panel, and different polydispersity index on the right panel. So this, first of all, the mean square displacement in these ABP or in active system, it shows, if you ignore this very early time, which is actually because of overdamped dynamic, but starting from this point, it actually shows the initial crossover from the ballistic to the diffusion. This is as line 2, and super diffusion to diffusion, and this is a slope 1. And as I am increasing the activity, this crossover time changes, and this is for a fixed polydispersity, and that result is known. That is present even in this polydispersed system, and that's not surprising. Okay. And then we actually define the dynamic diffusivity dt, which is simply the delta T by 4T, 4 because of D is equal to 2. That also shows that the diffusivity increases as I am increasing the activity. That is again from this first plot. But if I am tuning my epsilon, the polydispersity index, for constant V, then mean square displacement shows some variation. But if I look at this dt, that actually zooms this plot, then we find that for the higher polydispersity, the diffusivity is higher in the steady state compared to for the zero polydispersity, and which is again not very trivial why the polydispersity will increase the diffusivity in the problem. Okay. Now we look at it for different packing, because the packing should matter, because maybe you can say for the lower density maybe something else happening, and for higher density, or for very high density, yeah, obviously it will go to some jamming state that we are not looking. But we look at the system for 3 different packing density, 0.65, 0.75 and 0.85, and after 0.85 system might go to jam state, but we have not looked at for that characteristic with respect to polydispersity. So this is the effective diffusivity, which is defined as the late time limit of this dt for different, as a function of activity for different polydispersity, different curves, and for all of these packing fractions, this d effective goes as v square, which is already known in the literature that the effective diffusivity is proportional to v naught, or the activity square in the system, and that all these curves are actually more or less going as v square. So this dashed line is a slope 2 for all polydispersity in the system. Then we actually also plotted d effective as a function of polydispersity for different activity, and these are the different colors are different v here for increasing v from the black to the magenta, and for different packing fractions again, and we find some nonlinear curves, and actually all of these curves can be fitted very well with this expression here, where this v to the power beta, the beta is the exponent known is close to 2, because if epsilon is 0, then it's actually governed by this term only. So this is 2, but there is some kind of a scale function, exponential epsilon by epsilon c, which depends on activity, and this and all of these curves are actually fitting quite well with this expression. Then we try to extract by this fitting this epsilon c, and if we rescale my x-axis with respect to this epsilon c and y-axis by v to the power beta, where beta is 2, then we find a very nice scaling collapse of all the data for 3 different packing densities, and this alpha exponent for all 3 packing density we find close to 0.2 in this and this shows actually this feature is present for all these packing density and for this range of polydispersity index and for different activity in the system. Okay, this first thing is that we found that there is an enhanced diffusivity, and this diffusivity can be obtained from this kind of some function which is valid for a wide range of this epsilon and v. We also try to see how much percentage change in the diffusivity we are getting for different packing density. That this is a delta D measured with respect to the zero polar dispersity for different packing density 0.65, 0.75 and 0.85. For the small packing density, the percentage change is maximum we found for the largest polar dispersity is close to 50%, but for the highest packing fraction, almost the diffusivity is doubled by increasing the polar dispersity in the system for such higher packing density. That basically says that in my system, I am not feeding more activity, but the dynamic in the system is much enhanced because of this polar dispersity or the inhomogeneity present in the particle level. Okay. Now we try to explain why this is happening because that doesn't look very trivial. So we try to measure the, now we have actually divided my particles in two categories. There is a mean radius. The particle above the mean radius I'll call them bigger, and the below mean radius I'll call them smaller. And by defining the Vi, which has in the denominator Ri or the particle radius, the bigger particles are effectively having the lower activity and smaller particles are effectively having the higher activity. Everything else is same for all both type of particles. But it's varying in a continuous fashion, but in a broad sense. Then we measure a quantity which we call as the mobility order parameter, and that is actually we measured as the number of rattlers. And how I am defining the rattlers? If some particle is surrounded by less than 3 neighbours, which is actually a very well valid way of saying in the monodisperse, but we adopted the same thing here. If it is surrounded by less than 3 neighbours, then it's a rattler. If it is more, then it's not a rattler. So we measured this T, which is a ratio of this, how many rattlers in my whole system, the fraction of rattlers. And then in the steady state, we have a time series of this, and using that we measure the probability distribution of this psi for different polar dispersity in the right panel and for different activity in the left panel. If I see for different activity, for the smallest activity, which is the black curve, we see that this psi t or the mobility order parameter, if the number of rattlers is more, I am expecting the more dynamic in the system. So we find that this for the smallest activity, the distribution is towards the more right. That shows that there are more rattlers, but we know for the small activity there was a less dynamic in the system. The system was less dynamic, diffusivity was smaller. But for the higher activity, shifting towards left, although it's converging slowly, but it's shifting towards less. Although the rattlers, number of rattlers is decreasing, but the diffusivity was higher. So then to further explain that this is because this is a counterintuitive, so then we just look at the second quantity, which is psi bs, which is the ratio of the number of rattlers which are big and the number of rattlers which are small. Now this is like a fraction of particles, bigger particles which are rattler and fraction of particles, smaller particles which are participating in rattler. And then when we plotted the probability distribution of this psi bs, then we find that for the smaller activity, this is more towards right. It means the bigger particles are more in the rattling state compared to the smaller particle, and for the high activity just reverse. That basically from here only says because by increasing activity the diffusivity was increasing, but but the smaller particles were contributing, bigger particles, it looked like the bigger particles are having the more participating in more rattling state. It means the bigger particle contribution in enhancing diffusivity is not much, and the smaller particles which are actually playing a major role in enhancing the more dynamic in the system. Then we look at the system for different polar dispersity index. Here we find in the same trend as in the data. This probability distribution of psi shows that for the smaller polar dispersity, this peak is towards the smaller value, and as I am increasing polar dispersity shifting towards higher, it means number of rattlers are increasing and the dynamic is also increasing in the sample. And if I look at this quantity, then it's actually shifting towards left. It again shows the smaller particles are contributing more into the dynamics of the system compared to the bigger one. And this is again the dimensionless activity, which shows that the smaller particles are more motile, or maybe the having a higher activity compared to this larger one. Okay. Then this is just a snapshot to show that at different polydispersity, how the rattlers are arranged. The blue are rattlers and the red are the non-rattlers. We also look at the steady state structures in the system, not only the dynamic. So few things are very trivial also. When the polydispersity is 0, one should get the MIPS, because we are at very high density and activity is also such that if I may plot the radial distribution function of particle, then it shows periodic oscillations, and there are large distance oscillation that shows that there is a HCP structures and all. So that is MIPS signature. As I'm increasing polydispersity, these oscillations are actually suppressed and they are actually distorted also, because there is no longer a periodicity present in my problem, in my system. Then we also try to look at the number fluctuation, which I started in my introduction, but this number fluctuation not just to show the configuration or the steady state, the density in the area, but it can also give the measure of how frequently in the box the number or the density of the particle is changing. If I look at this delta n by n to the power half, I normalized here, so that if it is like equilibrium phenomena, then this number should be, this flat line should be present, the one line here. For the zero polydispersity, we are going to get MIPS, and this cluster is very almost static. Then this delta n is by n to the power half is actually decreasing with n. That means it is a smaller than n to the power half. And till some extent it does the same, even the red one. If I increase my polydispersity, then it's actually going parallel to 1 or maybe slightly increasing. But for the higher polydispersity, it's actually getting much larger than n to the power half, and this exponent is actually close to be found is close to 0.4 in this. This is actually 0.4 roughly. This number fluctuation also tells that there are clusters and they are more dynamic, because in a given area of the box, the density is changing in my sample. Based on that, we have drawn the phase diagram in the activity, dimensionless activity, and this is actually the mean activity versus the polydispersity index for 3 different packing densities. So let's focus on this right panel here, rightmost. So for this small activity and the small polydispersity, it's a kind of a monodisperse and the less motile system. So we find that there is kind of one can say like there is a very less dynamic in the problem, and just one thing, yeah, very little dynamic in the problem, and there are some structures present in the problem, and that we call as the solid jam phase. As I'm increasing my this polydispersity, but still this activity is kept to small numbers, then I'm actually going to the phase where there is a motility is small, the particles are not moving much, but they are not very dynamic, and that we call as the liquid jam phase. And then in this region where the epsilon is small and the activity is high, that is actually the limit for the actually 0 epsilon will be the completely an MIPS phase. So this we call as the MIPS liquid phase. And this region where both the V and the epsilon is high, we find there is an enhanced diffusivity, and this number actually shows the value of the diffusivity for the magnitude of the diffusivity, enhanced diffusivity, and there is no periodicity, and that we call as the pure liquid phase, which is actually the reason is the most important reason in our study. So with this, I would like to conclude. The first part I already said. The second conclusion is that the polydispersity enhances the effective diffusivity in the collection of ABPs, and there are also other aspects of the problem can be seen. The one key conclusion I can say from here, at least to this intrinsic inhomogeneity, we have introduced both like big and small particle, or the higher activity and lower activity active particles, as well as in the disorder, in the bond disorder, less aligned and more aligned. But effectively the outcome is that the positive result is enhancing and giving the output, and negative is suppressed in this intrinsic inhomogeneity scenario. And I'm actually looking forward for the experiments to test these findings. Yeah. Thank you. Questions?
Yeah. You want it?
I can hear at least.
Okay.
Give him.
As far as I understand, when you have when you have this bond disorder Vichek model, the transition you find is first order, right? Again.
No, bond disorder. No, there in our model or in some other, no, the transition is then okay. It's not exactly Vichek. It's a Vichek with vector noise. Vichek alignment plus vector noise. So there are some like questions like about angular versus vector noise that I have not went through.
What is the order of the transition then?
Even in the Vichek model, the transition is continuous, provided you go to the larger system and then you find that it's a first order phase transition.
Okay, and do you? I mean, there is a particular thing about the I mean, first order phase transition. You have a phase coexistence region.
Yeah, phase coexistence is there. Yeah.
And then in the Vichek model, you have microphase separation. Means when you put it in band, you see.
Yeah.
And that you see in the disordered model too.
That we see in the disorder model. Yeah, that we see in the disorder model.
So you have.
We don't see the band formation in the disorder model.
You don't?
We don't see the band formation in the disorder model. There is no macroscopic clustering. There is a homogeneous density I showed. No?
But so I'm confused. So
Let me just go to that picture. Yeah, this one. Although I have not shown very clear band, but we can see there is a very high dense clusters in this. The numbers are much larger, and compared to this one where we don't see such.
is that in the phase coexistence region?
This is near transition. This picture is near transition.
Now, what I mean is essentially when you vary either noise or vary the density, then sort of you go, since it's this first order phase transition from gas region, via a phase coexistent region to a liquid region. And you do not observe, so there is no critical point because it's first order. So there is a region. In this region, do you observe this region too?
Yeah, that's what actually we have not shown that series or time series or snapshot, but that can be seen from here. If I measure the order parameter as a function of time, and using that if I measure the probability distribution of order parameter, for the pure, like without disorder, it's actually bimodal, order and disorder coexistence. But with epsilon, there is no such coexistence.
Okay.
That we do see, yeah. Yeah, any other?
For the polydisperse case, for the polydisperse case where you had calculated the effective diffusivity, you had found a scaling structure. Is there any theoretical reason to expect that particular scaling function, or it was a purely numerical finding?
We just found it's behaving like exponential and we just wrote that. We were trying to find out something in the literature, but we could not. But it fits very well.
Because if I take this v to the beta term out, then what I am
It's
left
a scale,
with, that is just the mean
scaling
free path,
function, yeah.
effectively. So
Yeah.
that's what I was. Is there any reason to expect that effective mean free path should look like that? That's what I was.
I don't know.
thinking.
Maybe you can give the reason. I don't know.
No, I don't know.
I don't know. Yeah. Okay. Thank you.
Instead of the polydisperse system, if we have a monodisperse system and we change the self-propulsion velocity by epsilon plus or minus epsilon, so can we expect the same results as the polydisperse?
That's what the actually referee asked us. We need to check it. We expect we will get, but I am not very sure. Some things you will not get because what you are saying, if I just change the activity, then I'm only changing the dynamics, but the structures or the packing will not change. The phenomena which is appearing because of packing the results, that will not be present there because everywhere there is a periodicity. But some feature might be, but we don't know the answer right now. Yeah.
Any other questions? If not, we'll take a 5-minute break and come back for the next
Okay,
talk.
thank you.